Hello and welcome to EE233. I'm your TA Blake Wingard, and in this video we're going to be looking at the combinations for our numerical library. Before we get started, this one depends on the factorial functions covered in a previous video, so if you have not implemented those, please go back and do so. With that being said, first we need to discuss what a combination is. And a combination is simply the number of sets you can create with a given set of items where order does not matter. Taking the math mumbo jumbo out of that, imagine that you had a deck of cards. Scroll down a little bit here. This actually should be an example here. Here we go. So a standard deck of cards is 52 cards. And if you were to be dealt 5 cards, such as the case of a Texas stud or poker hand, yada yada, whatever game you call it, then you should be able to create 2,598,960 combinations. Okay? We'll be coming back to that later to grab whatever formula we need for it. Starting out, we should handle our switches. And so they won't change much from the factorial. As a matter of fact, we already even have n, but we do need to include one additional argument, that for k. So in order to keep our comments, this one is for factorial. And I'm going to go ahead and add a tab to each one of those. And then this one will be for combinations. So in addition to the input for n, we should have the input 3, or argv3, as an input for k. Alright, let's go ahead and add that on. We will be utilizing the same steps. As a matter of fact, we can just simply copy this whole block of code. Make sure we get everything on the right line. And so instead of calling factorial, we'll be calling combination. In this case, we'll use v1. Remember that our argument count should be bumped up to 4. And let's go ahead and throw in one more variable, k. And so instead of just capturing the inputs k, we're going to be capturing the inputs n and k. Again, the function is now combination. Combination. v1 n, comma, k. And we'll go ahead and simply grab that. Copy it here. Replace each one with %d like we did previously. And in this case, we're returning an integer because the values won't be getting so large. So we need to come along and instead of calling it results, we'll go ahead and call it combinations. So replace everywhere you have results with combinations. Okay. Don't forget to capture your k. It should use the same method as n, only being at argv3 instead of argv2. Alright, with all that said, we are one copy and paste away from having our switches set up. Let's come along and change all our version 1s to version 2. And then let's update our help a little bit. Okay, combination, combination. And since we already know from the Wikipedia link what 52 and 5 should be, we'll just use 52 and 5. For V2, there is the interesting case of where you would have them being the same number. I don't know if it's listed here, and I don't want to scroll too much. But for the sake of discussion, if you had 4 objects and you want to know how many combinations you could create using all of those objects, then it should be just 1. Alright? Like in the last video, I like to print out the function name. So we'll grab that real quick. This is just to ensure that we are calling the right function, just as a bit of a sanity check. Don't forget your new lines like I did. Okay, and then let's bring up our command line after we build it. Good, build successful. Let's navigate to your build, or I should say your project directory. Debug, MinGW. Stretch this out a bit to make it bigger. And checking our directory, there it is. Go ahead and call help, still works. And then let's try combination V1 with 52 and 5. Alright, cool. And then V2 should call V2. And it looks like we are set up good up there. So, combinations. Luckily, it's not too convoluted. As a matter of fact, we already have a predefined function. So I'm going to bring that over here and type it in for the rest of you. So our combinations V1 uses the equation n factorial is divided by k factorial times n minus k factorial. Luckily, we already have our factorial functions, which we'll be utilizing 2 things. We'll be using factorial V1 for combination V1 and factorial V2 for combinations V2. Alright, so let's create a couple temporary variables. We know we should have a results variable that we return later once everything is said and done. And then let's create a couple of temporary variables to make things easier for ourselves. So we're going to use double to capture the n factorial. Again, double because the factorial returns doubles. We're going to need k factorial. And then we're going to need the n minus k, which I will refer to as nk factorial. First thing to note is that this equation is defined only when n is greater than or equal to k. Otherwise, it is 0 when k is greater than n. So let's go ahead and handle that. So according to Wikipedia, if k, actually, before we do that, there is one other problem. N and k could be negatives, in which case that would be an error. So what we want to first do is ensure that k or n are both non-negative. I'm sorry. That should not be less than 0. They should be positive exclusively, meaning not 0. So, if n is less than or equal to 0, or k is less than or equal to 0, then we have an error. So, error n and k must be positive integers. Okay, and then we will print out what n was and what k was. So n, comma, k, print out the help, and we will set the results equal to -1 to indicate there was an error. So remember that if k is greater than n, according to the article here, then it is 0. So results equal 0. And finally, we get the proper spot where everything is all well and good. And so what do we do? The first thing we should do is calculate the n factorial. Remember that this will be the 1. Then we should calculate the factorial of k. And finally, we should calculate the n minus k factorial. All right. Once all that's done, our results will be n factorial divided by k factorial times nk factorial. This may or may not work. As a matter of fact, we're just going to run it. And that should be combinations. I don't know if I had that misspelled or if I just accidentally deleted it. But this might cause an error depending on how lucky we get. So if we run as it is now, then this should produce that 2,000,059 whatever. Okay, let's bring up that Wikipedia because I don't remember what the number was. And as you see, we are 1 off. The reason has to do with a bit of rounding error. And to fix that, all we have to do is round the function up to the nearest integer using the ceiling function. Please note that you must include math.h in order to use the ceil function. Okay. Let's try this one more time. Sorry, that was from a previous test. And there we go. Now that matches what it should. 2,598,960. And let's go ahead and test our edge case. So if they're the same, it should be 1. And then if n is less than k, should be 0. And if one of them is negative, we get an error. And it tells us what the values were. All right. Now setting up our, wrong spot. Moving on to our V2, it's essentially going to be identical. Only everywhere you see V1, change it to V2. Let's build it. Come back to the command line. And now let's test each one with our V2. So the 52.5 produces our 2.5 million. Let's do 3. So that should be 0 because n is less than k. Let's do the same. That's a 1. Let's make n negative this time. N and k must be positive integers. N was -5 and k was 5. All right. And let's go ahead and throw in a 0 just to test that. And there you go, must be positive integers. And that is essentially it. You can come along here, comment out these name printouts, for you don't need them anymore, unless you just want to keep them. With that being said, I hope you found this video helpful. If you have any questions, feel free to email your professor, and thank you for watching.